candidate for U.S. Senate in New York. These wildfires, I had asked my guests about preparing a discussion of this after we were covered in soot and smoke from the fires that were devastating Canada. Now, unfortunately, we have a tragedy unfolding on the island of Maui with dozens of people dead, hundreds of people missing, towns leveled, and the media generally spreading hysteria about man-made climate change, as opposed to taking a responsible scientific approach to not only the causes of these fires, but the causes of weather, of climate. And the point of that is what mankind can do about it so that we don't suffer loss of life as a result. Loss of human life due to extreme weather is greatly reduced over what it was a century or two ago, because we have better architecture, better infrastructure, better forecasting. But nonetheless, we've seen horrible tragedies in countries that are not developed, like Haiti or in China before the Three Gorges Dam was built, etc. Now, part of the solution is to understand the way our universe operates. And I can report that today, Russia's Luna 25 launched at 2 a.m. Moscow time. So I guess that would have been yesterday, our time. And that is going scheduled to have a soft landing on the moon coming up, I guess, on August 21st, just before the BRICS summit begins in South Africa. India launched their Chandra mission also to have a soft landing on the moon, which is scheduled to land, I believe, on the 23rd of August. You see the BRICS nations not only meeting to discuss a potential new economic architecture, security architecture, how they're going to expand since 40 nations are interested in joining them, but also they're working on discovering things about our universe that will make it president who clearly is not really calling the shots, and the complacent Congress, where you have a few people resisting the policy of continued unlimited money and weapons to Ukraine, provoking a war with Russia. And I can report that this past Sunday I was a speaker at a rally sponsored by Humanity for Peace, which is a true coalition and included presidential candidates actually from the Democratic Party in the person of Robert F. Kennedy Jr., who addressed experts like Scott Ritter, Garland Nixon. Also, there was a short video greeting from there were importantly speakers from Guinea, Conakry at a Ghanaian American Friendship Association, a candidate for president of Haiti, and a leader of a major Islamic organization, and also, I should say, founder of Trends Journal, Gerald Celente, also from the state of New York. I thought the rally was extremely effective and significant, being there at the United Nations on August 6th, the 78th anniversary of the bombing of Hiroshima, which was done by the United States for no reason except a geopolitical one. And then there was another event 3 days later on the 9th of August, the anniversary of the 850. The producer Heffelfinger, who has produced a film about this, extremely moving because of the question, not only the bombing, but the question of forgiveness for something really hideous that one experienced personally, so that you're not crippled by that, but that mankind can have perhaps move beyond feeling the necessity to terrorize people into submission, as opposed to appealing to human reason because you were trying to do things that are ultimately good for mankind. So I'm not going to say more, I will introduce our first guest, Rob. Good. Bob should just go ahead, and I'm going
Okay,
to see if I can do something about my internet connection.
okay, see if I can share my screen here. Okay, let's see. Okay, start this. Okay, well, thank you for having me on, Diane. Um, I actually sort of thinking through this presentation. Um, I was thinking in terms of all of these phenomena that we're going to discuss here in terms of forest fires, the question of extreme weather events, whether you're talking about drought, the conditions under which you have flooding. Ultimately, you're looking at the question of the relationship of the Earth to the sun. And I was thinking about something that you think about what mankind knew about the sun, say 150 years ago. The mankind knew that it was this big hot ball up in the sky. Nobody knew, what actually allowed the sun to generate the energy, that the heat and the light that it generated. Um, so certain discoveries that were made that allowed a breakthrough to occur, including on the one hand measurements of spectroscopic measurements where you take the light coming from the sun, or you can also take the light coming from other stars and break the light up with a prism into the different frequency, and see that you actually have very discrete lines at very specific frequencies, not just a wide, broad variation of light with increasing continuum of energy. And then the whole question, what, why does the sun appear in the sky the way that it does? It's a big, yellow, very hot ball. Actually, it was only a little bit over a century ago that there was a discovery made by Max Planck, and also Einstein had a certain role in this, that discovered their conception of what should be going on when you have what was called a black body. You take a body and you heat it up to higher and higher temperatures. Their conception was you have more and more energy available for the emission of light. Therefore, the intensity of the light at any particular frequency of light should be increasing. And as you go to shorter and shorter wavelengths or increasing frequencies, this curve of intensity should basically take off like a rocket. And essentially, this created a real crisis. And what was required is the breakthrough that Max Planck made, that also Einstein had a certain role in, realizing that ultimately there has to be a certain limit to the you cannot partition energy out, cut it down into smaller and smaller pieces. There has to be a smallest quantum of energy in which the light is packaged, so to speak, and this allowed the people to actually understand why the spectral curve of the sun or other hot bodies have the shape that they do. So, that understanding, created the basis for understanding also, you have a certain amount of radiant energy emitted from the sun, and this radiant energy, when it comes to the Earth, some of the light is absorbed by the gases in our atmosphere, so that hopefully and thankfully we don't have ultraviolet radiation, very damaging, hitting the surface of the Earth. When the energy is absorbed by the Earth, it essentially has to re-radiate that heat. If the Earth is not going to just heat up and heat up and heat up, the amount of energy coming into the Earth has to equal the amount of energy being radiated out into space. Although, unlike the sun, the Earth radiates that energy at a very much lower temperature, so it's not visible light that's radiated out into space. It's actually light in what's called the infrared area of the spectrum, light that you can't see. And the sort of backdrop to this discussion is the question of, in fact, the Earth has been warming over the last century and a half. And the contention is what is behind that warming. And in fact, one of the speakers at the conference in Strasbourg, France, at the beginning of last month actually went into this. And essentially, the contention is, is it carbon dioxide? Is it something else? And ultimately, I would ask people to take a look at those presentations, and just want to proceed here. So we have a situation in terms of the North American continent. Yes, you do have a large number of wildfires. This is a map produced by a NASA-associated group, and you can see the distribution of the wildfires in progress. So what's the phenomena that's behind this? What can we understand of what's happening here? So I want to first start with this phenomenon people might have heard of, might be familiar with or not, called the El Nino Southern Oscillation, that the sunlight coming in the Earth's atmosphere warms the surface water of the, in this case, the Pacific Ocean. And there is a, okay, it actually left out some slides here. Yeah, there is a process under which you have the ocean surface temperature. It can have three different states. In this case, the recent period from May 29th to the 6th of August of this year, basically the period that we're in right now, you can see the brown, reddish colored areas. These are areas where the water surface temperature of the water is significantly warmer than areas where, for example, the color is blue. Okay, you can see the temperature scale below. So the top map is the beginning of that interval, May 29th, and then the shift that occurred until basically quite recently, a few days ago. If you look at this process over a longer period, I didn't put in the slide I hoped to put in. You have a normal state, so-called, of the oceans, where...
Yeah, I am sorry to interrupt, but Bob, would you mind clicking the slideshow button so we can see that bigger?
Oh, you can't? Oh, hold on.
Well, I mean, it's not full screen, right? If on the lower right of your screen, there's a number that says 67%. To the left of that is a slider.
Oh, okay.
To the left of that is a little picture of a slideshow.
Okay, so just click on the slide.
Please go left. Left. To the left of that slider. Please go to the left of that slider.
Okay.
On the bottom of the, never mind.
Oh. Okay. Okay. So basically, you have the ocean having three different states. In this case, we're looking at the beginning of what's called the El Nino period, where you have warm water, basically the middle of that both of those charts is around the equator, where you have warm water that piles up off the west coast of South America. And as the El Nino develops further, that can become larger amounts of warm water that pile up there. At a certain point, this process reverses, and the way this is explained is that you have the trade winds that go from the east to the west, and the normal condition is that the trade winds would move the warm water on the surface of the ocean to the west towards the Australia and the Pacific. That at a certain point, that would be the neutral area, where this red area, instead of being right up against South America, it would be more central or even towards the western part. And then there's another condition that develops where you have not just the ordinary condition of the trade winds, but the trade winds become more intense. And instead of having simply this warm water concentrated in the western part of the Pacific and normal temperature water near the coast of South America, the piling up of warm water in the western part of the Pacific, increases the depth of the warm water in the ocean, gets deeper. And what begins to happen is cold water from deep under the surface of the ocean begins to well up, and the water piling up on the western coast of South America becomes cold water. This is the phase. It's called La Nina. So this whole people are talking about with this. So I just want to sort of just briefly go through some of the implications of this. So this is the central line being the equator. You have warm water. In this case, you're looking at an El Nino condition. The warm water, the water evaporates. As the water rises, it cools, and you have the condensation of water vapor, so you form clouds. And then the air circulates and begins to fall. And as the air falls and is compressed, is at a higher pressure, it warms up. And so you have the distinction between areas where the air is rising and you have the formation of clouds. These are the low pressure areas, and the area where the air is falling and the air pressure at the surface is a greater pressure, and you have clear skies. Okay, so this circulation, the air can not simply go up vertically and move along, so move towards the pole. So if you look at, here's the equator, what we saw before, the air is rising along the equator, and then it can go towards the poles. But something happens here, because at the equator, the Earth is turning. The great circle of the Earth at the equator has a bigger diameter, a bigger circumference than any other circle of latitude. For example, at 45 degrees latitude, instead of going 1,038 miles per hour, the motion of the rotation is only 733 miles per hour. And yet the air that's rising into the upper part of the atmosphere and wants to go north, it has the momentum that it had when it was traveling along the equator. So instead of going directly north, the momentum causes it to bend towards the right. And in other words, the Earth is rotating slower underneath it than the air is moving itself. So this phenomenon ends up creating a condition where you have these actually two jet streams are formed. You can think of all the area along the ocean are places where you could have evaporation in this process that we looked at in terms of air rising, and then the air that goes towards the north, it can't go directly towards the pole. It has to bend and ends up being funneled into these jet streams. So there's one jet stream, subtropical jet stream, and similarly, look back here, you have air that's in the jet stream also can descend from the jet stream. And as the air descends, it becomes warm. So the areas underneath this subtropical jet stream are high pressure areas. So these are areas where you have clear skies. And then once the air descends and wants to move north, again, the same question occurs. You can't go directly towards the poles. It has to bend towards the west, towards the east. And this is the phenomenon that creates the jet stream. This is just sort of an indication that it's actually a quite broad area. The air is traveling most rapidly at the center of the jet stream, and then the lowest point here might be 10,000 feet, so it's still pretty far up from the surface of the Earth. So here is a weather map with the present locations. This is actually a map for tomorrow, so it's basically based on present conditions and what they think is going to happen. These red arrows are the location of the, in this case, the polar jet stream. And you see this map, you have these little Zs there, areas where you have lightning, thunderstorm activity. And if you think about wildfires, the conditions for wildfire is number one. You want conditions that are dry, that are not just simply dry, but also the question of if you have allowed dead trees to sort of accumulate and you have a lot of potentially combustible fuel and that's not cleared out, that creates the conditions where the right conditions occur, then you can get large wildfires. But the other thing is this question of the lightning, and that I may mention a little bit more about later. So now let's look at what the latest North American drought monitor map that includes the data for Canada and Mexico is actually from about 5 weeks ago. But you see the present conditions, the areas that are yellow are the areas that are abnormally dry, the first stages leading towards drought. So you see these characteristic patterns. And in fact, if you look at these North American drought monitor maps and sort of month by month over in a period of time, it's quite interesting in terms of the question that you want to ask is why do the patterns develop the way that they do? Is there a way to understand the processes that are underway so that we can forecast what's happening, and potentially if we understand what's happening, there might be certain things that we can do to intervene in this process. In terms of one aspect of it clearly is the question of controlling water resources, water that's already on the Earth's surface, which such things as diverting water into reservoirs, that sort of thing. But also you have the question of what happens to the air it's in the atmosphere. How do you create the conditions where you can actually shift those patterns? So that's the most recent North American drought monitor map. Now, what we saw before the cycle, this is a map of the recent cycles, and I want to sort of look at what these North American drought monitor maps look month by month. And I'm going to start actually in the last couple of months of 2014. So that would be this part of the chart, which is blue. That's the part of the phase called La Nina, where the water up against the west coast of South America is cold water that's upwelling from the ocean, and the warm water has been moved very far towards the Western Pacific, and then move into the part of the chart where you have this red area where the water is warm and is piling up against the western coast of South America. So just start here. So this is September 2014. You see what the overall condition is. Just go through this bit by bit, and you can get the general pattern. Okay, now that's roughly where at the peak of that, at the maximum of the El Nino chart that I showed before, and continue a couple more months. Okay, now, so anyway, it's difficult to say just looking at this patterns what's going on. Is the El Nino La Nina cycle causing these variations? There's very difficult just to say by looking at a pattern. So the question is, how do you actually approach this question? Is actually look at it from the standpoint of how do we develop an understanding of water management, which over the mankind's history up until the last 50 years, mankind developed a lot of understanding in terms of how to move water that's already on the Earth's surface. And basically, the idea is looking at statistical patterns of how much rain falls in a certain area. You can say, okay, we can expect that sort of pattern to continue unless something disrupts it. But there hasn't really been until perhaps recently, and there may be work going on in this area that I'm not able to think about. How do you actually create the conditions where it might be possible to intervene on the processes shaping this process as a whole? Okay. Now, just going back just briefly to this question of the wildfires, this is the number of the blue bars is the area burnt by wildfires in Canada, and it's over a relatively short interval. It's from 1980 to the present, basically. And if you think about the maps I just showed you, from 2015 into 2016, there's no clear indication that even under conditions where what looks like increasing drought, that all of a sudden, as a result of that, you have a big outburst. It's not just the question of the dryness, but it's the other aspects of this involved. As I said, if you have conditions where you have a lot of fuel built up that hasn't been cleaned out, that's creating the conditions where, for whatever reason, whether it's lightning or whether it's human caused, that can break out. Okay, and this I just the most recent data in terms of what the area of this really. Let's look at what was revealed by this character Anthony Watson in an article. If you look at what was publicly available as information by one of the agencies up until 2021, the record of the number of wildland fires in the United States, the number in this case of acres burnt, you see that the present, sort of slow increase in the wildfire activity is not unprecedented when you look at what the actual history is. So that's important to keep in mind. And he says, okay, what they basically did is they took the lowest point of this historical. This is something called the Palmer drought index for Canada. This is basically in the last couple of days, August of this year. The red areas are areas where you have significant drought, and the orange and yellow are less severe. The blue and purple areas are areas, okay, and similar map for the United States. They call it the Palmer Drought Severity Index. So in the top area here, the yellow is a certain minimal amount of a drought and then increasing intensity, and blue is soil that has sufficient, if not even too much moisture. So let's just look at what I'm going to show you next is the western part of the United States, basically from about here, measuring how much of the area of the western part of the United States had at least the first stages of drought, at least yellow, if not red, orange, or brown. So that's what we're looking to look at here. So this irregular rectangle here is the area that we're looking at, and it's what percentage of that entire area has drought conditions, minimal drought or more severe drought. And what we're looking at here is not just the last 20 years or 100 years. This is based on a study by Cook and his associates going back to 800. Now, obviously, from year to year, 1 year percent or 80% of the area of that western part of the United States has minimally a certain amount of drought. The next year, that might collapse down to 20%. So it's very episodic. But what this black curve is if you take essentially do what's called that. So you see this black curve. So over the interesting thing about this is sort of off the chart here. Can't. Okay. The interesting thing is from 1900 to 2000. I mean, people think about the Dust Bowl in the 1930s. The average for the United States has some minimal area of drought. So if you look at the long-term pattern over a 60-year interval where you're averaging it, that 1930 period doesn't even stand out because the areas, both in time and area of the United States were significantly. The interesting thing is it looks like the last 500 years have been relatively wetter than the previous 700 or 800 years that are here. You have actually times when you have mega droughts that lasting almost 200 years. Okay. So the question is, what do we actually do about this? I didn't have time in the last minute to just pull some of the slides I wanted to use. I came across a very interesting paper put out by someone based out of Singapore that puts forward a hypothesis that's very interesting in terms of what might be happening with this El Nino phenomenon. And if I'm going on too long, maybe you can tell me how much time I have.
And have your face larger.
Okay, I can stop sharing. Is that what I do?
Yeah.
Screen sharing, stop share. Okay. Yeah. Okay.
Great.
Yeah. Because you're dealing with a phenomenon, obviously, that whether it's forest fires, whether it's drought, in some cases whether it's flooding, it's a catastrophic event. You're sort of limited in what you can do. So this paper that I came across develops a very interesting hypothesis. He says that, look, the Earth has, yes, a gravitational field in terms of what we looked at before in terms of these weather patterns. That's one aspect working there. But also the Earth has an electrical potential difference between the surface of the Earth and the ionosphere. And actually one of the drivers of that difference in electrical potential is thunderstorms. In the thunderstorms, you have snow crystals that, if they're in the upper part of the thunder cloud and the temperature is below a certain critical value, the electrical charge on the snowflake will be positive, or maybe it's negative. I'm not sure which way. But once these thunder clouds become essentially generators of an electrical potential difference, and this is why you have the phenomena of lightning, and you have not only just lightning from the thunder cloud to the Earth, there are also interesting phenomena of essentially a different kind of lightning that goes upward towards the ionosphere. It's in the Earth's magnetic field, but it's also in electrons will be moved in the direction towards the west. Now, this is something occurring up in the upper ionosphere, but since the ions bump into other ions, they bump into other neutral molecules in the atmosphere. This causes a drag on air lower down, and essentially over the course of the solar cycle, you actually have a change in the altitude of the ionosphere. It gets higher or lower, and this changes the electrical potential difference. And this is a certain point, or the strengthening of the trade winds in the case of the El Nino phenomenon. And he also says that if the question that charged particles from the sun are not able directly, the Earth's magnetic field sort of shields them, but they're able to funnel. The difference between the two cases is in the North Pole, if charged particles come in, there's a basically uniform distribution of land masses around the Arctic Ocean. So there's no particular concentration of charge in one area versus another. Okay, but in the case of the South Pole, if this electrical charge is deposited in Antarctica, and you look at the proximity of Antarctica to the southern tip of South America, and that ocean water is conductive, he argues that of South America, and whether this is borne out in terms of a hypothesis or not, he says that has certain significant things that you could do if that is the case in terms of intervening to be able to control this process or at least forecast it. So anyway, that's what I would say for the moment.
All right. Well, thank you very much. We have now also Jason Ross, who worked with Mr. LaRouche's science team or basement team for many years. And Jason, why don't you share your thoughts or response to anything Bob has presented?
Well, I think what Bob has shown us, among many other things, is that there is a lot to learn and a lot to know about our planet, about our climate, about weather patterns and things like this. And that we are so badly served by a green ideology that tries to chalk it all up to, climate change. Something bad happened, it must have been because of climate change, because everything was perfect before we came on the scene or before we industrialized and emitted CO2, which is a big pile of crap. As you pointed out in your introduction, Diane, weather-related deaths are way down, like an order of magnitude down over the past century because we get better at creating our own environment. The external environment or the natural, the unimproved, the standard model environment matters less and less to us because we're interacting more and more with an environment that we create. If we have irrigation systems and flood control and electricity and roads and sidewalks and plenty of storage for agricultural products, refrigerated storage, good transportation, we're interacting with this network that we've created rather than with, a forest on its own or like, an unimproved river. And so the kind of knowledge about processes like what Bob described, the very exciting potential for altering in some ways some aspects of weather, such as rainfall, one of them in particular, I think points to our need to continue to improve our mastery over, our control over, our ability to do something better with the world around us than what it is on its own. And so just to say one more time that the green ideology goes exactly against this. Supposedly it's to protect us from the ravages of nature, but the effect of it is to make us more vulnerable to them by preventing development and by lowering, on the whole, the energy intensity.
Thanks. So I'll just open it up just in the way of questions and comments. Someone posted on Facebook that the governor of Texas it's outrageous. I mean, sometimes you think that things are done to just create maximum hardship and difficulty and chaos. But I thought, Bob, if you can go back, one of those charts of the drought, going back to, I guess, the year 800, it looked like the year 1200 was exceedingly dry. I don't know if we have any records of what was happening with forest fires, but I don't believe there were too many automobiles in the year 1200 or major factories or cows farting or any of the things that they tell us are causing climate change. But maybe you could go back and also just take one of those charts and say what the years are, because it's a little hard to see the years. They're very tiny.
Yeah.
So people can see the fraud of this.
Okay, where am I here? Yeah, that's it right there. Anything I can do to move this over?
You can also go to where it says view on the top and change it to slideshow. I think it'll give you a bigger one. And
You,
top in the red bar.
it's sort of buried under the black bar. Hmm.
Oh, you don't have access to that. Oh, because probably the
Yeah,
screen share thing is in the way.
yeah,
Okay, don't worry
yeah,
about it.
yeah. So here, the medieval droughts, that's roughly 850 AD, extending up to about 1050. Okay, and then again, starting about 1150 roughly, extending up to 1300. As I say, this is you're eliminating the high frequency events, so you don't see the change from year to year, and it's averaged over 60 years. But the striking thing is, it does seem that the last 500 years is wetter, if you want to call it that, than the 700-800 years before that.
What does the height of the red indicate? Why?
Well, again, what you're measuring is how much of the land area of that western part of the United States, the area in that rectangle I showed, how much
Yeah,
of that total area has minimally some degree of drought, whether it's
okay.
yellow or more severe. So,
So it's
40%.
telling you area.
Yeah, yeah, and so that doesn't mean you don't have drought. Even in these areas that are blue, you can still have drought, but the relative amount of drought is less in these areas. It's less than the average over that whole interval. And as I say, if you look at this shorter with the high frequency events, you might have some of these areas might be 60% drought, but it's not that significant when you look at the longer time span. It's only a brief interval, and the rest of the time is relatively wetter.
So the end of the chart is the year 2000. It doesn't show.
Yeah, it goes to 2000. Yeah,
Right.
and
The Dust Bowl years.
yeah, although you do have an increase from 1900. It's not 1930 that's the peak, but so I guess you could say this is an increase of aridity, but it's not comparable to this at all.
Right. So I think this really indicates, as Jason was just saying, there's a lot of factors going into this that we don't fully know or understand.
Yeah. I've seen one paper that again, the problem is they're taking a relatively short interval, maybe 30 or 40 years, and they claim that if you look at not only the El Nino cycle, but also what's called the Pacific Decadal Oscillation, which I think is in the northern part of the Pacific, and you also look at the temperature, that they claim that this allows you with relatively a good correlation to say what areas of the United States are likely to have drought. But again, that's sort of a statistical approach. It doesn't really tell you, okay, what do you do about it?
Right. Okay, I think you can stop the share. Well, I would like to hear from both of you what to do about it. And I also would like to hear your thoughts on NWAPA, the North American Water and Power Alliance, which was something, from the 1960s, actually. Senator Robert Kennedy of New York. Sir LaRouche was a great supporter of it, but then he raised the question later that perhaps we were in an unseasonably wet period, and maybe it wouldn't function in the same way that it was designed, or you might have to account for other ways of generating more water, like ionization or nuclear desalination or things like that. So what do you propose? What should we be doing to avoid these disasters?
I think part of it is this question. For example, in the Pacific Northwest of the United States, it also hit Vancouver. Now, if NWAPA had been built, the dams would not have been in any position to capture that water. So I think that's sort of an example. Because when NWAPA was scoped out as a project back in the 1950s and 1960s, people didn't think in terms of this phenomenon of atmospheric rivers. Our ability to have ability to measure these kind of phenomena today and potentially to do something about it, the kind of ionization techniques that have been used by some people to increase precipitation, where you basically have a high voltage a wire and you're emitting ions into the atmosphere. The ions actually become centers for hydration. Water vapor from the atmosphere condenses upon the ion. This releases a certain amount of heat, and the air mass is warmed and it rises. And this has found some success in terms of increasing the precipitation in areas which were arid and statistical increase. But potentially you could also use the same kind of phenomenon to cause the very tiny microscopic droplets in, for example, an atmospheric river to condense and to cause the precipitation to occur before landfall. So it becomes a question of water management. If we can say, okay, there's this atmospheric river coming at it, looks like it could be dangerous. Why don't we sort of intervene to at least, mitigate the damage? Or, for example, consider how much of the water resources of the United States are dependent on hurricanes or tornadoes coming in to the United States. Now, if you sort of think of the processes that are shaping the weather, you have this, as we saw before, the radiant energy from the sun is most intense in the equatorial areas. So those are the areas of the planet that are hottest. And so weather is a way in which you can redistribute the thermal energy from the equatorial regions into the polar regions, and that develops in a very particular way because of the laws of physics. But is there a way of intervening to, for example, prevent a tornado or a hurricane from having devastating damage? And in fact, Sergei Poulinets pointed to the example of, I think it was Hurricane Katrina, where you had what's called a four-bush decrease, which is a decrease in the intensity of the cosmic radiation reaching the Earth. And this caused a change. The cosmic radiation that intercepts the Earth's upper atmosphere becomes, like I was saying, in terms of this ionization, the cosmic radiation becomes, which are charged ions, they become centers for precipitation of water vapor to form these microscopic droplets, which become the basis for rain. And what happened is that this decrease in the intensity of cosmic radiation resulted in a colder temperature in the Earth's upper atmosphere, because you weren't condensing water vapor onto the ions, so the latent heat of the water condensing wasn't being generated. And this increase in the temperature differential caused an increase in the intensity of the hurricane. And there's also been an example where, for example, using these ionization apparatus in the pathway of such a tornado, it shapes the environment, which in some cases actually has decreased the intensity of these phenomena. So are there things like that we can do to intervene? Because I don't think we can stop the hurricanes and tornadoes if we wanted to, but also if we could, it would mean you wouldn't have the water. So is there a better way to get the water into the country than hurricanes, or at least minimize the damage?
Well, yeah, I mean, for those who may not be familiar, a thumbnail sketch of the NWAPA project, the North American Water and Power Alliance, was a proposal to take surface water from rivers in Alaska and Canada and to reroute it through natural geographic trenches, and also with pumping and new canals as needed, into the western parts of the United States, the southwestern part of the United States, and even into northwestern Mexico as well, to really unlock the agricultural and overall civilizational potential of these regions that have got, a lot of them have really ample sunlight, the soil's fine. What's missing for the updates to that with today would include the fact of higher power intensities with nuclear energy, for example, to help with pumping that water more effectively. Along coastal regions, desalination to supply water, at least if you're near the coast, and for urban use, you can do that pretty effectively, especially again with if you have high quality power like nuclear power, and eventually to address the really bad job that nature has done in allocating water resources across the continent is the right way, going right into the ocean. No one's doing anything with it. Think about these poor water molecules. They've gone through so much trouble. They've been evaporated. That can't be fun. They've rained down, they've fallen on the earth, and then now you're just going to let them go right back into the ocean? Wouldn't it be better if they got to take part in growing a delicious nectarine or, walnuts, or for irrigation and agriculture? You get a real multiplier effect. Because these plants, they're in the water, even if you do drip irrigation, they're all emitting water out of their leaves. I mean, this is part of just what plants do. So, that ends up improving and changing the local environment as well. It causes some more local extremes that you see. The drought and the extreme temperatures are all moderated. And look, this isn't a someday maybe this would be nice to expand kind of thing. This is something that we have to do, or we are going to, look, we're starting to run out of water. A lot of the United States, especially the central part of the United States, drawing from aquifers. Some of these aquifers in certain areas, they refill just fine. So their aquifers like the Ogallala are being drawn down. You have to go deeper and deeper and deeper to get the water. It increases the energy costs of getting it. And of course, it just means that we're running out. So the approach isn't to say, well, let's stop irrigating in enormous quantities to ensure that it's available for us.
Exactly. And that's a lot more fun. I mean, that gives you a child a reason to exist, because we're going to do these things to improve nature. So I think that's I'd like to share with our audience.
Well, I think if you look at any large water project, for example, I've looked at a certain amount of this question of the Columbia River Treaty signed between the United States and Canada, which opened up the development of the Upper Columbia River, the building of the dams on the Upper Columbia River, which actually, if you look at the history, this was, at that point, you had a premier of British Columbia, W.A.C. Bennett, that was, I don't know, a lot of people have told me in terms of if you talk to engineers that, okay, well, that was, back in the time of FDR, you could never do something that way. In one sense, something like, for example, the Columbia River Treaty, the development of those dams, you required a feasibility study. Now, I think we still require a feasibility having too much water. Just ask people in British Columbia that, last November were hit by this atmospheric river. But the question is there a way of keeping it under control? And is there a way of demonstrating to people, if we build this, it's going to have some knowable result that we're not going to get into trouble? I think that's, you do management that includes the atmosphere. And that also, if you wanted to bring together the people who could do such a feasibility study, that would bring in the people like Sergei Poulinets, who knows a lot more about these questions in terms of the Earth's elect than I do. Because it's a scientific problem you have to solve. And that can also excite the general person and the people in the population.
Right. Well, it's a lot more fun than trying to change other naturally, happily on the planet with a higher standard of living. I mean, the point really is the greatest sense of smell. He was in a research facility where they're looking at dragonflies and the antennae are for some reason. But the point is we make the world better. Human beings make the world better. We are intrinsically good. And if you look at, going back to what I said at the beginning, Russia is about crusty, cranky, old, rotten imperial system of a tiny handful of elites who think that everyone else has to do what they say. Well, the rest of the world doesn't see it that way, and they're not listening anymore. And they're not under control, which is the reason why we are in danger of nuclear war, because that may be the only way to stop 6 or 7 or 8 billion people not to be slaves and subjects anymore. So I want to thank both of you for joining me this evening. I hope people listening have found some things to be provocative. I hope you go and do some research and begin to think of how exciting it is that we live on this planet Earth and the kind of things that we potentially could do to improve our planet contribution